Hi, my name is Senta Jansen, and I'm studying to become a doctor in optics. That's a science about light, and I'm working with lasers. Today, though, I would like to talk a little bit about waves, what they are, how they work, and why they're important to us.
Near a road, you may have seen a speed camera or one of these displays which shows how fast a car is travelling. These send out light waves, which reflect back from a moving vehicle. The reflected waves are then detected, and the speed of the vehicle can be calculated and shown on the screen. This is how you can use waves to measure speed, and later we'll find out how to measure the speed of the waves themselves. Now back to Senta in the lecture theatre.
Another situation where you might have come across waves is when you've seen someone in the gym using those battle ropes. So you can create a wave by flicking this rope up and flicking it down again.
I'm transferring energy to the rope by moving the rope up and down to then create a wave. The waves travel away from me at 90 degrees to the rope's motion. These are an example of transverse waves, just like water waves or light waves. Waves transfer energy from one place to another. The waves that I'm making here travel along the rope to the end. But what happens if you get a reflection?
This is a Rubens tube. It's been developed by two German physicists in 1905 because they wanted to visualize waves. We've got a metal tube and we've got a gas inlet here, which fills the tube with camping gas. This here is the signal generator we're using to introduce a sound wave into the Rubens tube. What you see here is the wave that we introduce. You can see the resting position, it's this line here, that's the undisturbed position. And the amplitude is the point of maximum displacement from the undisturbed position here. You can also see the wavelength. The wavelength is from one point of the wave to the equivalent point on the adjacent wave. For example, you've got the peak to peak, or trough to trough, or you can choose any point on the wave to the equivalent point on the adjacent wave. So this speaker generates a sound wave that travels through the Rubens tube. It gets reflected on the side and travels back. So inside of this tube, there's a standing wave. And because there are holes on the top of the tube, the gas can escape. When we then set fire to the gas, you will see a high point when the pressure inside of the tube is high, and a low point where the pressure inside of the tube is low. And now let's set it on fire. So we've got a standing wave in the tube where there's areas where we've got high pressure and the gas can escape, so you get a high point on the wave. And then the areas around here when you've got a low pressure and the gas can't get out as much, therefore you don't have a flame. When we change the frequency on the signal generator, we see how it's moving, and we create a different standing waves where it has now the high points and the low points on a different location.
Waves travel at different speeds in different media. For instance, light travels through air differently to other materials such as water or glass. But we can calculate how fast a wave is traveling with the following equation. V equals F times lambda. Let's look how to work this out. So V is the velocity or the speed of the wave. It's measured in meters per second. F is the frequency of the wave, which is how many waves pass a point in 1 second. This is measured in hertz. For instance, if 10 waves pass you in 1 second, then the frequency of the wave is 10 per second, or 10 hertz. And finally, lambda. Lambda is the length of the wave. It's the wavelength as we saw on the oscilloscope. And the wavelength is measured in meters. If you multiply the frequency and the wavelength together, you can find out how fast the wave is traveling. Remembering the wavelength is across two peaks of the standing wave due to the reflection. Our frequency in this case is the pitch of the note we are playing through the speakers. Now multiplying them together, we get the speed of the wave.
Instead of using a signal generator to create a standing wave inside of the Rubens tube, we can also use an alternative. Dr. Bill Brocklesby.